So, I want you to look down at your hands for a second, like really look at them.
Yeah, just take a good look.
Right. And, feel the solid wood of the desk you might be sitting at. Every instinct you have tells you that this world is just made of solid stuff.
Of course it does. And that's
Right.
our entire daily experience.
Exactly. But mathematically, scientifically, according to the source material we're looking at today, you are almost entirely empty space.
It is a profoundly counterintuitive reality, isn't it?
Yeah.
We spend our entire lives interacting with what feels like this unyielding, dense physical world, but the raw numbers tell a completely different story.
And I want to welcome everyone to today's deep dive into this specific source, because the mission here is to figure out this exact mystery. Like, how do we know atoms are real? Why is the classic atom model wrong? And, well, why do things feel solid if they're not?
It's a huge topic.
It is. And the source material actually provides this unbelievable visual to put the true scale into perspective. I mean, I love this analogy.
The stadium one.
Yeah, the stadium one. So imagine scaling a single atom up so its center, the nucleus, is the size of a standard glass marble.
Okay, a marble.
Right. Now, take that marble and set it right in the middle of a massive sports stadium on the 50-yard line. The outer boundary of that atom, the electrons, they would be way out by the highest seats in the grandstands.
Just hovering way up there in the nosebleed.
Exactly. And everything in between that marble on the field and those upper deck seats is absolute total vacancy, like nothing at all.
And that staggering proportion applies to literally everything. The screen you're looking at right now, the chair you're sitting in, the cells in your own body. Matter is just overwhelmingly a void.
Okay, let's unpack this, because that brings up the big driving question. If I am mostly nothing, and the desk is mostly nothing, why doesn't my hand just pass straight through it?
Right. Why does empty space push back?
Yeah, why does empty space feel hard?
Well, that illusion of solidity is kind of the ultimate mystery we're unpacking
Right.
today. But, before we can even explain why empty space pushes back against your hand, we really have to trace how humanity managed to discover this invisible architecture in the first place.
That makes sense. We can't solve the solidity mystery without knowing what matter actually is. So how did we figure out that atoms are real when we can't even see them? I mean, thousands of years ago, before microscopes or labs, people were already arguing about this, right?
Oh, absolutely. The Greek philosophers around 400 BC were really chewing on this. They proposed that if you took a piece of matter and just kept cutting it in half over and over, you'd eventually hit a wall.
Like a fundamental limit.
Exactly. They imagined this hypothetical indivisible unit that they called atomos, which literally translates to uncuttable.
Uncuttable, right.
But, I mean, they reasoned this out purely from logic. They just felt reality couldn't be divided infinitely. However, that was competing with a very intuitive counter theory championed by other thinkers that matter is just a smooth continuum.
A continuum. Like, meaning you could just keep slicing it forever.
Yeah. The idea was that if you had an infinitely sharp knife, you could just keep slicing a drop of water forever and ever, and it would always just be a smaller, continuous puddle of water.
Which, I mean, that sounds completely plausible if you're just looking at the world with the naked eye. Water looks continuous, smoke looks continuous.
It really does.
So how did we actually move from this ancient philosophical debate in Greece to hard scientific proof?
Well, the breakthrough didn't come from, building a better magnifying glass to look closer. It actually came from chemistry, specifically from weighing things.
Weighing things.
Yeah. In the early 1800s, a scientist named John Dalton started meticulously weighing chemicals before and after they reacted. And he noticed this stark, completely unbreakable pattern.
Okay, what were the pattern?
Elements always combine in fixed, simple whole number ratios by mass.
Oh, I see. Let me visualize this to make sure I grasp the mechanics here. If I have, say, 10 grams of oxygen and I want to make water, it will only ever react with a very specific, rigid amount of hydrogen.
Exactly.
So say it needs exactly 1.25 grams of hydrogen. If I toss in 2 grams of hydrogen, that extra 0.75 grams just sits there completely ignored by the oxygen.
Yes, the chemical reaction just stops cold.
Yeah.
The oxygen absolutely refuses to absorb any more hydrogen than that strict mathematical ratio dictates.
So what does this all mean? I mean, if matter were a continuous, smooth paste like some of the Greeks debated, elements should be able to blend in any random, messy proportion, right?
Right, you could just mix them endlessly, like stewing different colors of paint together.
But because the oxygen only pairs with an exact amount of hydrogen and just ignores the rest, they must be pairing off like like dance partners.
That's a perfect analogy.
Like one discrete unit of oxygen grabbing two discrete units of hydrogen. When there are no more dancers on one side, the music stops and the mixing just ends.
And that dance partner mechanism is really the only logical explanation for Dalton's arithmetic. Chemistry proved that matter comes in these discrete blocks that snap together in specific quantities. Basic math, not a microscope, forced the atom into reality.
Which is deeply fascinating and kind of ironic, honestly. Chemistry proves these uncuttable blocks exist, so physics immediately decides to try and crack them open.
Naturally. Yeah, the era of the uncuttable atom officially ended in 1897. That's when J.J. Thomson discovered the electron.
And the electron is what, exactly?
It's a particle, thousands of times lighter than the atom itself, and it carries a negative electrical charge. Now, since atoms as a whole are electrically neutral, Thomson deduced there had to be some positive charge hiding in there to balance things out.
Right, you need a positive element to cancel out the negative electron so the whole atom stays neutral.
Exactly. So he proposed what's known as the plum pudding model. He pictured the atom as this diffuse, spongy sphere of positive charge, that's the pudding, with those little negative electrons embedded inside it like plums.
A squishy, continuous blob of positive charge.
Yep.
Okay, but that implies if you shot something at it, it would be like firing a bullet into a cloud of dense smoke. It would just go right through.
Right. Which brings us to Ernest Rutherford's laboratory about a decade later. They set up an experiment where they took a source firing alpha particles.
And alpha particles are like microscopic bullets, right?
Exactly. Heavy, highly energetic, positively charged microscopic bullets. And they aimed them at an impossibly thin sheet of gold foil.
So, based on Thomson's plum pudding model, those heavy, fast-moving positive bullets are encountering a diffuse, spongy positive cloud.
Which means they should shred straight through it. They shouldn't even slow down. A spongy cloud of positive charge just shouldn't have the dense concentrated mass required to deflect something moving that heavy and that fast.
Did they go straight through?
Well, the laboratory setup involved these researchers literally sitting in the dark, waiting for their eyes to adjust, and watching for tiny flashes of light on a zinc sulfide screen to see where those bullets landed.
Wow, tedious work.
Incredibly. Now, most of the particles did sail straight through, exactly as you'd predict. But a tiny, rare fraction of them bounced back at severe angles. Some even rebounded almost straight back at the source.
And Rutherford famously said this was as incredible as if you fired a 15-inch naval artillery shell at a sheet of tissue paper and the shell bounced back and hit you.
It completely shocked them. The sheer violence of that deflection just shattered the plum pudding model entirely.
Because the only physical way an artillery shell bounces off tissue paper is if there is a microscopic, impossibly dense boulder hiding inside the tissue.
Exactly. That was the big takeaway.
So all the positive charge and almost all the physical mass of the atom isn't a diffuse sponge at all. It is entirely concentrated in an unbelievably tiny central region.
The nucleus.
Right. Most of the alpha particles missed it because the atom is mostly empty space, but the bullets that scored a direct hit collided with a brick wall. That's how they found the core of the atom without ever actually seeing it.
Yeah, that violent laboratory experiment gave us the core architecture of the modern atom. At the absolute center is the nucleus, packing in the protons. Those protons carry the positive charge, and their count acts as the absolute identity of the element.
Like 1 proton is always hydrogen, 6 is always carbon, and so on.
You got it. And we also have neutrons packed into that dense center. They are neutral, carrying no electrical charge, but they add significant mass.
So if you change the number of protons, you get a completely different element. But if you just add a neutron, it remains the exact same element, just a heavier version.
Correct. That's called an isotope. Those heavier isotopes act identically in chemical reactions, but that extra mass crammed into the nucleus can make it unstable.
And that instability is what causes the nucleus to slowly decay, which is the precise mechanism radioactive dating uses to calculate the age of ancient artifacts and fossils, right?
Exactly right.
Okay, so that's the center. Then way out in the empty space, orbiting this dense core, are the negative electrons. If you add or remove one of those outer electrons, the positive and negative charges are no longer perfectly balanced.
Right, which gives the whole atom a net electrical charge, turning it into an ion. But I want to pause on something you just said.
Oh, what's that?
You mentioned the electrons orbiting the core. That brings us to the classic science classroom poster from 1913.
Oh, yeah. The heavy nucleus acts like the sun, and the electrons orbit around it in neat, perfect little circles, just like planets in a solar system.
Right. It's the universally recognized symbol of atomic science.
I mean, I have that image burned into my brain from middle school.
What's fascinating here is it is universally recognized and it is completely, undeniably incorrect.
Wait, why is it wrong? It makes perfect sense visually.
It fails due to a foundational, unbreakable rule of classical physics. An accelerating charged particle must radiate away its energy.
Hold on, I need to push back on that for a second. When I am driving my car around a circular track at a steady 50 miles per hour, my speed isn't changing. I am not accelerating.
Your speed is constant, sure, but your direction is constantly changing. In physics, any change in velocity, which includes a change in direction, is technically classified as an acceleration.
Oh, I see.
Because an electron is moving in a circle, it is permanently accelerating. And since it carries a negative charge, classical physics dictates it must constantly bleed off energy in the form of electromagnetic radiation as it turns.
So if it's bleeding energy just by the act of turning, it would lose the fight against the positive magnetic pull of the nucleus. It wouldn't stay in a stable orbit. It would inevitably spiral inward and just crash into the center.
In a tiny fraction of a second. If that solar system model were actually accurate, every atom in the universe would have collapsed into itself almost immediately after forming.
Well, considering you and I are sitting here breathing air and talking, and all our atoms haven't collapsed into microscopic black holes, classical physics must be missing a massive piece of the puzzle here.
It was. Classical physics essentially predicted the immediate destruction of the universe. To save the atom, scientists had to throw out those old rules and step into the strange, probabilistic mechanics of the quantum realm, completely redefining what an electron actually is.
Okay, so how does quantum mechanics stop the spiral of death?
By discarding the idea of a travel path altogether. Electrons don't orbit. They don't have definite continuous positions. Instead, they exist in orbitals, which are these three-dimensional probability regions.
Probability regions, what do they look like?
Some of these regions are spherical, some look like dumbbells, others are these complex multi-lobe shapes spanning out into the empty space.
So it's not a tiny moon zipping around a track. It is a fog of maybe surrounding the nucleus. The electron isn't moving from point A to point B inside that fog. It just exists as a spread out likelihood until it interacts with something.
A literal cloud of probability. And to prevent that cloud from collapsing into the nucleus, quantum mechanics introduces quantization. Electrons can only exist in specific, discrete energy states.
Okay, I often hear this compared to a ladder, where an electron can be on the first rung or the second rung, but absolutely cannot hover in the empty air between them. But why? What physical mechanism forces them to only exist on those specific rungs?
The latter is a common visual, yeah. But a better way to understand the underlying why is to look at a guitar string.
A guitar string, okay.
When you pluck a guitar string, it vibrates in standing waves. You can have a wave with one peak or two peaks or three peaks. But because the string is firmly pinned down at both ends, it is physically impossible to have a wave with 1.5 peaks.
Right, the wave would just cancel itself out and simply fail to exist. The physical math of the string doesn't allow for a fraction of a wave.
Exactly. Because an electron in the quantum realm behaves as a wave, its probability cloud must form a perfect, continuous standing wave around the nucleus.
Wow.
It can vibrate at frequency 1 or frequency 2, but it physically cannot exist at a frequency of 1.5. Those forbidden intermediate zones simply cannot support the electron's mathematical wave.
That mechanism makes so much more sense than a ladder. It is acoustic resonance. So they leap instantaneously from one valid wave state to another by absorbing or emitting a photon of light with the exact amount of energy needed to bridge that frequency gap.
Yes, and because these valid wave states are completely unique to each individual element, the light they emit creates a highly specific wavelength.
Here's where it gets really interesting for everyday life. This is exactly why sodium street lamps have that harsh, distinct orange glow. That orange light is the visual signature of sodium electrons dropping between their specific resonant quantum wave states.
It is the identical mechanism astronomers use to analyze stars trillions of kilometers away, too. Every element projects a spectral fingerprint, like a unique barcode of light generated by its specific quantum wave states.
So the quantum wave states give us glowing street lamps and allow us to map the chemical composition of entire galaxies. That's incredible. But back to the collapse problem.
Right.
If they are constantly stepping down these resonant wave states, shedding energy as light, why don't they eventually hit the absolute bottom and crash into the nucleus anyway?
Because there is a fundamental lowest frequency the wave can maintain, known as the ground state. Once an electron reaches that ground state, there is simply nowhere further to fall.
It just hits the floor.
Yeah, it cannot lose any more energy because no lower wave pattern can physically exist around that nucleus. That mathematical limit guarantees the absolute stability of the atom.
So the universe is basically saved by a baseline vibration. The atom is a dense core surrounded by a massive empty stadium, inhabited by a ghostly probability fog that strictly obeys quantum wave rules.
You summed it up perfectly.
Ah.
Which brings us back to our central mystery.
Right. If you are mostly empty space, and the wooden desk is mostly empty space, governed by ghostly probability fogs, where does the physical sensation of a solid surface actually come from? Because solidity clearly isn't physical stuff violently colliding with other physical stuff.
It's primarily electromagnetic repulsion. The outer boundaries of all your atoms are those electron clouds, which, as we established, carry a negative charge.
Okay.
As you press your hand against the wood, the negative clouds in your skin approach the negative clouds in the desk.
Like trying to push the negative poles of two strong magnets together, they forcefully push back.
Exactly. At a microscopic range, that repulsion is intensely strong. When you rest your arm on the table, your atoms are not actually making physical contact with the wood's atoms. You are perpetually hovering on a microscopic cushion of electromagnetic force.
But wait, earlier we established that an electron is just a fog of maybe, a probability. How can a mathematical probability exert a physical magnetic force that physically stops my hand?
Well, in quantum mechanics, the probability isn't just our lack of knowledge about where a tiny particle is hiding. The electron physically manifests as that spread-out cloud of charge. The negative electrical charge is literally smeared across the entire probability region.
Ooh!
Yeah, so when two of these smeared-out fields get close, the fields themselves repel each other.
So I am officially hovering on a field of smeared-out charge.
You are. But the source material mentioned a second, subtler reason for solidity, beyond just magnetism.
Oh, right. What was the second factor?
It comes from the Pauli exclusion principle. Electrons belong to a class of particles called fermions, which obey a very strict quantum law. No two electrons can occupy the exact same quantum state simultaneously.
Meaning they absolutely refuse to share the same physical space, energy level, and wave pattern.
Yes. If you try to force two atoms together past their electromagnetic repulsion, their electron clouds would be forced to overlap. Their electrons would have to assume the same quantum state. And the universe categorically prohibits this overlap from occurring.
So the rules of physics act like a concrete wall. It is not a repulsive force like magnetism pushing them apart. It is just the sheer mathematical impossibility of the overlap existing.
Exactly. That categorical refusal generates an effective resistance known as degeneracy pressure. And it is incredibly potent.
The synthesis of this principle is staggering, because this exact same quantum rule, the refusal of electrons to share a state, is the degeneracy pressure that holds up a massive white dwarf star, preventing it from being crushed by its own astronomical gravity.
It's amazing to think about. The exact same mechanism stopping your hand from passing through the desk stops a dead star from collapsing into a black hole. Empty space governed by rules becomes perfectly rigid.
Empty space with rules can be perfectly rigid. It really leaves me wondering about our daily relationship with this invisible world. We are hovering on force fields of ancient, impossibly tiny probabilities. Can we ever actually hope to interact with this microscopic realm directly?
We routinely interact with it now, but to grasp how, we really need to feel the agonizing scale we are dealing with here. A typical atom is about 1/10 of a nanometer across.
Okay, 1/10 of a nanometer.
If you look at a single millimeter mark on a standard ruler, you could line up roughly 10 million atoms side by side across that tiny gap.
10 million inside one single millimeter.
To put it another way, there are more individual atoms in a single glass of water than there are glasses of water in all of Earth's oceans combined.
It's a realm of existence so numerous it just defies human intuition entirely. And visible light is practically useless here, right?
Completely useless.
Because the physical wave of a visible light beam is hundreds of times larger than an atom. So using light to see an atom is like trying to feel the fine texture of a grain of sand while wearing a giant, thick winter glove.
That's a great way to put it. You simply cannot resolve the image. We had to invent a way to perceive them without light, which led to the scanning tunneling microscope, or STM.
How does that work?
Instead of looking at the surface, it feels the surface. It drags an unimaginably sharp tip, sometimes ending in just a single atom, incredibly close across the material.
But if they cannot touch because of the fierce repulsion we just talked about, How does the tip actually feel the surface?
It measures a quantum effect called tunneling. Remember how the electron is a fog of maybe?
Yeah.
Because it is a spread-out probability wave, that wave doesn't just halt at the hard boundary of the atom. It decays, sure, but it extends slightly into the empty space beyond.
So a tiny fraction of that probability fog actually bleeds past the physical barrier of the atom.
Exactly. And if you bring the microscope tip close enough, the electron's probability wave overlaps with the tip. Even though there is an impenetrable empty gap between them, there's a distinct mathematical chance the electron just appears on the tip.
It tunnels through the barrier without ever crossing the space in between.
Yes. And by measuring how many electrons casually pop across that gap, a computer adjusts the height of the tip to keep the flow constant. It reads the electrical topography of the surface, literally mapping the bumps of individual atoms.
That is wild.
The precision is so immense today that researchers don't just map them. They use the tip of the microscope to coax single atoms along a surface, arranging them one by one.
It's the ultimate paradox. No one has ever seen an atom in the ordinary sense of using light, yet we can pick them up and arrange them like microscopic building blocks.
It highlights the massive leap from the ancient Greeks debating philosophy to modern physics actually maneuvering the very fabric of matter.
It really does. As we wrap up this deep dive, I want to bring all these cosmic and quantum scales back down to you, the listener, because there is a profound final note in the source material about the actual atoms currently making up your body.
The sheer age of our component parts, right?
Yes, exactly. The hydrogen swirling in the water of your cells was forged minutes after the Big Bang itself. It is billions of years old. The heavier elements, the carbon in your DNA, the oxygen in your blood, the nitrogen in your lungs, those required immense pressure to form.
They were forged inside the crushing cores of ancient stars.
Stars that lived and died in violent supernovas long before our own sun even ignited.
And those ancient atoms have been locked in primordial rocks, they've drifted in ancient oceans, and they have built the tissues of long-extinct organisms over millions of years.
So to recap our journey today, you are a temporary arrangement of stardust. You are mostly empty space, you are incredibly ancient, and you are held together by probability fogs and force fields discovered barely a century ago.
It reframes completely what it means to be a physical being.
It changes everything. And I want to leave you with one final lingering thought to explore on your own. Building on this idea, the source states that these atoms are infinitely recycled and that nothing in you is new except the pattern. Well, if every single piece of physical matter inside you is just borrowed from dead stars and will eventually leave you to build a mountain or a raindrop or another person, then who you are isn't your physical matter at all. Your true identity is strictly the invisible, temporary software, the pattern, that is borrowing these ancient atoms for a brief cosmic moment. So, what exactly is the nature of that pattern?